Now let's look at another situation. Let's say that we have two springs again, but this time we have them side by side, connected to some mass m. And now let's see how far it's going to stretch. So once again, we look at our forces. So we see that we have gravity down. Now we have two spring forces going back up. So if we say that each spring has coefficient k, then we know that k is equal to mg over the change in x. We know that x is mg over k. But now if we look at our net force equation, we see that the force of gravity is equal to 2 times the spring force, right, which is 2kx. So in other words, x is mg over 2k. So if we say that d is the distance that it stretched with one spring, then we see that x is equal to d over 2. But then what this tells us for our spring coefficient k now is that k is mg divided by d over 2. So again, this is our effective spring constant, which is 2k, where k is mg over d is a spring constant with just one spring. So recall that we said that in series, k effective is going to be k divided by the number that we have in series. Now we see that in parallel, so if I have a bunch of so if I have if I have m springs all in parallel like this, then our effective spring constant is going to be m times k. So we see that for series we divide by the number of springs, and for parallel we multiply by the number of springs. Okay, and so now we're going to use the concepts that we talked about in the last two videos, the series and parallel springs, to talk about a realistic spring. So not just kind of these idealistic springs that we're using, but we're going to look at what happens if we have a more realistic situation.